Hi there, and welcome to this video on eigenvalues of a matrix. We just got through learning about eigenvectors of a matrix. So what's an eigenvalue of a matrix? Well, to get into this topic, let's go back to the original example we saw, this matrix 2, 0, 3, negative 1. What we learned about in the last video was the eigenvectors of this matrix, which are vectors such that when I multiply them by a, I get merely a scalar multiple of the original vector back. Multiplying by a doesn't move the vector significantly in R2. It just rescales it, either stretches it or shrinks it or completely flips it 180 degrees. So let's revisit some of the things that we learned about this matrix. I'm going to put some eigenvectors that we learned down here below. So one of the first eigenvectors we saw for this matrix was 2, 2. And I'm going to do a little scratch work up here in the top right to remind ourselves why 2, 2 is indeed an eigenvector. If I take this matrix times 2, 2, then what I get here is 4, 4. And what we notice is that this is just merely a scalar, namely 2 times the original vector. So multiplying by this matrix doesn't do anything bizarre to the vector, it just rescales it. Now, another vector that we saw from an example that was an eigenvector was 5, 5. And I'm just going to go up here to the original work and scratch out a few things, namely just this and some of the results that we had here. Leave that scalar spot open there, and let's just multiply by 5, 5 and see what we got. Well, see, that's going to give me 10 times 10, and that is going to be 2 times the original vector, 5, 5. So one thing to point out, and this is very important here, that not only is 5, 5 an eigenvector, it has the same scaling factor as 2, 2 did. And it's no coincidence that 2, 2 and 5, 5 are parallel to each other. They point in exactly the same direction. They were both pointing on the line y equals x, interestingly enough. And they were both eigenvectors with the same scaling factor, namely 2. Now, is something up here? Well, let's try one more sample here, a new example that we haven't seen. Let's pick another vector that also is parallel to 2, 2, or 5, 5, that lies on the line y equals x. Let's go with, let's say, negative 3, negative 3. Okay, that is pointing in the opposite direction of 2, 2, but it's still on the same line as 2, 2, namely the line y equals x. So I'm going to go and scratch out the details here and see what we get. Well, if I start with negative 3, see, this is going to give me a negative 6 in this one, and let's see, a negative 9 plus 3, that's a negative 6 in this one, and lo and behold, I have the same scaling factor times the original vector. So not only is negative 3, a new eigenvector for A, it's got the same scaling factor as every other eigenvector that it shares a line with. So that's interesting. Let's kind of hold on to that for a second. So I'm going to kind of cluster all these eigenvectors together. Now, there was another eigenvector that showed up in the examples from previous, and that was 0, 3. Let's go through and remember why that's an eigenvector for this matrix as well. I'm just going to get rid of all the stuff over here in the details. So when I take this matrix times 0, 3, what do I get? 0, 3. This is going to give me 0 and then a minus 3. So a different scaling factor this time, negative 1 times 0, 3. So 0, 3 is an eigenvector, but it has a different scaling factor. Now, let's see if what we're noticing for the first set of vectors is true for the second set. Namely, if I take another vector that lies on the same line as 0, 3, will it also be an eigenvector with the same scaling factor? Well, let's try it out. Let's go with, now the line that 0, 3 lies on is simply the y-axis. So I can just pick anything on the y-axis. Let's go with, say, 0, negative 5. Just for fun. And let me just erase this stuff up here and see what we get. Now, if I start with 0, negative 5, what do I have here? I have 0 in that component and plus 5 in that component. And lo and behold, that is negative 1 times the original vector. So I have another eigenvector with the same scaling factor as the vector that it shares a line with. So we have sort of two classes of eigenvectors here. I've got this group over here, and maybe there are more that have a scaling factor of 2. And I have this group over here, and there's probably more you can put into it, that has a scaling factor of -1. Every vector in the group is an eigenvector, but they all have something in common, the same scaling factor. So what we've noticed in the examples is actually going to hold true in general. Let's take this as a theorem and give a very quick proof of it. If x is an eigenvector for a, and that would mean that a times x equals lambda x for some scalar lambda, then what we're noticing here is that every scalar multiple of x, every scalar multiple of x, it's a vector that lies on the same line that x does, is first of all also an eigenvector for a. And not only that, it's got the same scaling factor with the same scaling factor lambda. Now let's do a quick proof of this. This is a very simple proof that we can do in just a couple of lines of calculations. So we're going to make some assumptions at first here. We're going to assume first of all that x is an eigenvector for a. So I'm going to let a times x equal lambda x. That's what it means for x to be an eigenvector for a. And I'm also going to start with a scalar multiple of x. I need that in the theorem here. So I'm going to call that y, and let's say that it's equal to c times x. Now what I want to do here is show that y is also an eigenvector for a, and that the scaling factor stays the same. So let's start here with a times y. What I'd like to do is show that ay equals lambda y, the very same lambda that we have right here. Well, a times y, what is y? Y is equal to c times x, so I'm going to just replace. And then one of the rules about matrix multiplication says that I can factor scalar factors all the way out in front. So this is c times ax. But what is ax? Well, ax is equal to lambda x. And now here I have two scalars in a row, c and lambda. I'm just going to pull that lambda all the way out in front and parenthesize the rest here. And then what's cx? Well, cx is equal to y. So here I have what I was trying to show here. I have ay equals lambda y. So every scalar multiple of an eigenvector is also going to be an eigenvector with the same scaling factor. So that scaling factor is pretty important. We might have many eigenvectors. There are actually infinitely many eigenvectors if you can find at least one of them because of the scaling factor that I can introduce. But there's only a few of these scaling factors. Okay, so for example, in the previous slide we saw a whole group of vectors that have the lambda equals 2 factor, and that group is actually infinite because I can include any vector that lies on the line y equals x. But there's only one scaling factor that lumps them all together. Likewise, this is a very large group here, infinitely many vectors in that group that have lambda equals -1. So it makes sense to focus on the scaling factor lambda because it classifies some of these eigenvectors. And here's where our main definition for this video is going to come from. So if ax equals lambda x for some scalar lambda, then focus on the lambda. We're going to say that that lambda is called an eigenvalue. Okay, not a vector, but an eigenvalue. It's a number. This is a scalar factor, so it's an eigenvalue for a. And we're going to say that x is an eigenvector for a. We knew that already, but we're going to add an additional layer of terminology onto this. Is an eigenvector for a corresponding to lambda. Corresponding to lambda. Okay, so this is viewing the definition of eigenvector from the scaling factor point of view. So we focus on the scaling factor and call that an eigenvalue. Again, value connotes a number quantity rather than a vector, and the x here is a vector that corresponds to it. So here are some examples to play with here. Back to our original matrix, 2, 0, 3, minus 1. So we know the answers to some of these. We know that one eigenvalue for this matrix is lambda equals 2. Okay, what are some of the eigenvectors that correspond to that eigenvalue? That would be, for example, 2, 2. We also tried 5, 5. And we now see that anything that lies on the line y equals x is going to work. Every scalar multiple of 2, 2. So I'm actually just going to draw that set of vectors. Every eigenvector on this line has an eigenvalue of lambda equals 2. Another eigenvalue we found was lambda equals -1, and we found several eigenvectors that correspond to it. 0, 3 was our one we first found, and then anything that's parallel to 0, 3, like 0, 10, and so on. So here's another line lines worth of eigenvectors. Every eigenvector that lies on this line, every vector that lies on this line is an eigenvector with lambda equals -1. So we can verify that a given number is an eigenvalue for a matrix if we can just find an eigenvector that corresponds to it. But what if we don't have an eigenvector that corresponds to it? What if we're just given a matrix, like a 2 by 2 or a 3 by 3 matrix? How do we go about even finding these eigenvectors and these eigenvalues? Well, that's the subject we're going to take up in the next video, so stay tuned. So what might be lurking in the back of your mind is, if I have a matrix that's square, like A here or something larger, how do I even go about finding its eigenvalues and eigenvectors? Well, we're going to answer that question in the next video, where we're going to prove that lambda equals 3 is not an eigenvalue for A. The general principle in that video is going to give us a method for starting with just a raw matrix and constructing its eigenvalues and eigenvectors. So stay tuned for that.